to introduce?
Yes, so folks, it's my great pleasure to introduce to you today Professor Ahmed Busnaina, who has a very distinguished career in nanoelectronics, nanomanufacturing. I mean, his CV, it's incredible. His work, he's very well known for all that he has done in the past in nanomanufacturing. And in fact, he is the director for the Center for High-rate Nanomanufacturing at Northeastern University in Boston. So yeah, I have known Ahmed since I was a professor there in a different reincarnation. So it's it's a great pleasure to actually, we have been collaborating very intensively in the last years. And in fact, now Professor Ahmed is working with us at NUS in two big projects in flexible electronics. And I suspect that his seminar today will reflect his current interests in that. So Ahmed, thank you so much for being here today, and we're looking forward to your seminar.
Thank you so much. Thank you so much. And thank you for giving me this opportunity to give a seminar. I gave a seminar about a year and a half ago, but I thought that we've done so much more work since then. So I thought I want to have a chance to share our work with you. So let me start, let me share my screen first. Okay, and hopefully this will work. Do you see the screen okay?
Yeah, looks good.
Okay, excellent. So today I will talk about, so first of all, I worked with the conventional semiconductor industry from 85 to 2005. So I worked on CMP, I worked on CVD, PVD, I worked on scaling from 5-inch to 8-inch with IBM. I worked on copper electroplating, I worked on yield enhancement, I worked on looking at defects in a variety of semiconductor processes. So, but 2004, 2005, we started looking at a new way. At that time, we had nanotubes, we had nanoparticles, and then 2004, we had the graphene. And we started looking, there must be a better way, an easier way to do manufacturing that allows us to use whatever material we want, especially nanomaterials. And also, it should be cheaper. And so we started thinking about that, and then we wrote a proposal to the National Science Foundation, and that's how we got the NSF Nanoscale Science and Engineering Center for High-rate Nanomanufacturing funded in 2004. So I'm going to talk today about a new technology for making nanoelectronics, and this is directed assembly-based high-throughput printing of nanoelectronics and sensors on rigid or flexible substrates. So I'm going to give you an introduction, which is mainly the motivation, why we're doing this, and then explain how does it work, and then talk about, we have more than one directed assembly approach, electrophoretic, convective interfacial, and fast fluidic. So I'm gonna briefly talk about each one of them, and then talk about the kind of structures that you can make using these techniques, and then talk about a few applications, and then talk about scalability and the concept of a fab in a tool. That means you have one tool that does everything for you. You did submit your design and you can print multiple layers, micro or nanoscale. And at the end, you got a wafer that has multi-layers, interconnected, done in one lab, in one tool. Okay, so so the motivation first. I worked in semiconductor industry back when a brand new fab would cost you 400 million, 500 million only dollars. Now we're up to 20 billion. TSMC, the new fab is going to be over 20 billion. So today's semiconductor fabrication plants are very expensive, up to 20 billion. They cost 1 billion to operate. They use a lot of power, they use a lot of chemicals and water. For example, a typical fabrication plant uses as much power in a year as 50,000 homes. And because of that, you can see this figure here. This is from The Economist, 2018. It shows the number of leading edge manufacturing firms. In 2001, there were like 28. By 2018, only 5 left. I can tell you who they are: TSMC, Global Foundries, Intel, Samsung, Micron. That's it. And so basically, it's getting too expensive for everybody else. IBM doesn't do manufacturing anymore. Advanced Micro Devices does not do manufacturing anymore. There are many, many companies that stopped doing manufacturing because of the high cost. Okay, so that's the first motivation. Another motivation is also security, of course. If you make your own, if you have your own foundry and you make your own electronics, then it's very, very secure, instead of sending it overseas or sending it somewhere else. Okay, so that's the first motivation. The second motivation is we want to be able to use any material to make our circuit. Okay, so we want to actually print any material on any substrate. So we want to print conductive, semiconducting, or dielectric materials, organic or inorganic, down to the nanometer scale. We want to interconnect all these layers. These layers could be silicon, could be polymers, could be sapphire, could be any other material. We want to leverage the properties of nanomaterials, 2D materials, quantum dots, nanotubes, nanowires, any other new material. We should be able to take advantage of that. We want to have a process that lets us use that easily and integrate that easily into whatever electronics we're making. At the same time, we want whatever process to be high throughput. It has to be high rate compared to conventional labs. It has to be faster. Also, it has to be very low cost, capital and operational cost. And that was our goal from the very beginning. So somebody says, well, you said printing. So how does your printing compares to the inkjet printing or 3D printing, like some people call it? Well, to look at it very from a very high level, inkjet printing or 3D printing usually use droplets, at least the ones that use ink. And these droplets, each droplet use hundreds, sometimes thousands, sometimes hundreds of thousands of particles, depending on the size of the droplet. And then basically your feature size is as small as your droplet. And also the inkjet moves, and so the mechanical accuracy is very difficult to make alignment. So far, the inks were limited to organics and metals. And so what we do is we make it very, very simple. Instead of doing droplets of ink, where the particles are inside the droplets, we go directly to the particle. We control the particle directly. And that means our feature size could be as small as 3 or 5 nanometers, because that's our particles. The particles we work with are 3, 5, 10, 20. We work with a large size of particles, but we have done a lot of work with 3 nanometer particles. Okay, so that means that you can do nano very easily. There's an example here where these are quantum dots, and you can see we put them in organized. This is done over wafer scale, but you can see you can organize them into a very small size. This is 30 nanometer by 30 nanometer. Each particle is 10 nanometer. Okay, so using this technique, there's the assembly. You can use a variety of mechanism for the assembly. I'm going to talk about that. So basically, you can print 1,000 times faster. In some cases, about 1,000,000 times faster than inkjet. You can print 1,000 times smaller than inkjet. The best inkjet you can buy today is 10 micron. We can go down about 1,000 times smaller. You can print 1 layer in 1 minute, a whole layer. There's no inkjet that moves back and forth. 1 layer takes 1 minute. It doesn't matter if it's nano or micro scale. Okay, so this is a video. I'm going to show you just part of that video that shows, at least has an animation for the assembly.
Here's how the process works. A robotic arm will load the template and blank wafers. The arm takes them to precision alignment stations so they will match up perfectly. The template is sent to an assembly module for the key part of the printing process. The template with its etched circuitry is dipped into a well containing nanotubes or other types of nanomaterials. When an electric current is applied to the well, the nanomaterials are drawn out of the water and adhere to the etched pattern like ink. The newly inked template is aligned to the blank wafer, and both are taken to the transfer module, where a pressure device presses the two together. In an instant, the pattern that was inked on the template is printed onto the wafer. And like a printing press, the process can be repeated to make as many wafers as you want from the same template. Here's how.
So this particular one is designed to print flexible electronics. So in this case, we're using a template. The template could have micro and or nano scale features. We use electrophoretic assembly to assemble the nanoparticles on the template, and then, as you can see here, this is the template. For example, the template is functionalized so that the silicon will be functionalized to be hydrophobic. The rest of it, gold or tungsten, will be hydrophilic. Then you do the assembly. In this case, it's nanotubes. And then once the assembly is done, the assembly takes about a minute. Then you do the transfer or printing, and that takes about a minute. And then you actually are ready to go to the next step. So this is high throughput. It's additive, of course, room temperature and pressure. This particular process prints on flexible substrates. You can use PET, you can use polyurethane, you can use PEN, you can use a variety of polymers. It's multi-scale, material independent. You can use metal, you can use semiconductors, you can use dielectric particles. We've used a variety of those. Very low energy consumption is just one tool, and very low capital investment. So this particular one is on. I'm gonna give you some examples later on, show you some applications. But we also have a process where you print directly on the silicon wafer or sapphire wafer or any rigid wafer, for example. So this is how you make interconnect. So for interconnect, you have vias in dielectric. This dielectric could be silicon dioxide or could be any other dielectric, or could be even a photoresist or polymer. And so here you put this substrate with the vias in, and you have a conductor at the bottom. This conductor could be everywhere or could be just under the vias. And then you apply about electric field about 2 volts. The assembly goes on. You end up with fully filled vias. And when you remove the dielectric, you see the vias look like this. Now you can do this. This is gold. You can do copper. You can do copper. You can do aluminum. You can do tungsten. You can do silver. You can do polymers, silica. You can do half gold, half PSL. You can do a variety of things. It's a very flexible process. And by the way, you can do a 4-inch wafer in about 30 seconds. So it's very, very fast process. So the question that we face is okay. So these pillars are fused without any annealing. And so the question is, how are there any voids inside? And so we took a TEM here, and this is 150 nanometers high and 50 nanometers wide. And as you can see here, there's only 1 grain boundary, and so it is polycrystalline. You can see the grains going in this direction and in that direction. This is 5 nanometers, so it is polycrystalline. It can be single crystal, and I'll show you results that show single crystal. Also, we've done thousands of interconnect, and all of them turned out to be single crystal metal. So that fuse without any voids or gaps. But the question is, okay, these particles are functionalized. For example, this gold is functionalized using thiol. So the question is, did that affect the conductivity of this structure? So we did an experiment again and compared the printed interconnect with electroplated interconnect, and then we use the Zyvex nanomanipulator inside the SEM, so you can land on each 15 nanometer pillar and measure the resistance directly. And so you can see here, we measure the resistance. This is the printed resistance, and this is the electroplate resistance. So it's pretty much the same. and we've shown that we can actually go down to 25 nanometer here. And we've tried copper, silver, aluminum, gold, tungsten, and it's all pretty much similar to material deposited using conventional technique, vacuum-based technique. You can do a variety of materials. These are gold nanorods, for example. This is cobalt. This is iron oxide. So you can actually make very small structures using a variety of materials. And those, when you are at that size, you don't need annealing. The particles anneal on their own. So let me talk about, I showed you one process, which is electrophoretic process. We have another process, which is in cases where you don't have a conductor, you don't have access to a conductor. So basically, you need to do an assembly technique without using or without applying an electric field. And in this case, we have used what you do is you pattern your substrate, or basically it could be your substrate without patterning. It could be substrate that has structures already. Then what you do is you put a solvent like IPA, and then you put the suspension, and then basically you just apply a little bit of heat. The particles assemble very nicely in the vias, and you end up with, it's very repeatable process, very fast process, and you'll end up with structures as you can see here. It's a very versatile process. And so here you see the same process here. You can see these are fluorescent silica particles. They're 30 nanometers in diameter, and this assembly took 5 minutes, but we've been able to do the assembly in 1 to 2 minutes. And these are silver pillars, for example. These are silver lines. So it's a very robust process and very scalable. And we call it convective because there's convection and there's interfacial forces at work here. The last one I'm going to mention is simply fast fluidic assembly process. So this process is very fast. All you do is you functionalize the wafer, and in this case, that means you apply photoresist, you do the functionalization, and then you remove the photoresist, and then basically you put it in a solution that has specific viscosity, specific surface tension, and specific particle concentration, and you can do the wafer in 1 minute or less. And then it comes out. You can look at it like this, for example. This is a silicon substrate, and this is silver. And I'll show you some more data on this. So this is a very fast fluidic process, and you can do. We deposited anywhere from 15 nanometer up to 1 micron, for example, thickness of the substrate. These are some of the examples. This is a source and drain aligned with a channel in between them. This is a close-up. This is a wafer. This layer is done in 1 minute, for example. And this is copper, and this is silver. You can see with different size and different gaps. The silver printed, we buy the silver, and this silver is about 3x of the bulk resistivity when you measure it. We also done silver using nanoparticles. And this turned out, this was just published in Advanced Materials. And when we did this, we can see that all the silver interconnects were single crystal. You can see here, all of them were single crystal. So this was done with the convective interfacial assembly. Now, metal is easy. The hard one is really the semiconductor. So this is a 2.6 semiconductor. Now we work on a 3.5 semiconductors. And this is annealed. This is not annealed. This is actually the particles fused under the interfacial forces and the assembly forces only. There is no heating required. This one, it was annealed. So these are the particles after printing, and this is after annealing. And when we anneal, we found out that we have large grain size. So the grain size here is about 8 micron in size, which raises the possibility that you can actually make channels that are smaller than this size that could be single crystal for transistors. Okay, so let's talk about applications. The first application is interconnect and metal lines. So here we work with a company with analog devices, and they wanted to do this pattern. and they wanted to do it over the wafer, for example, over actually many wafers, and they want us to print 3,000 for each wafer, for example, and measure each one of them, which we did, and the resistivity was about 3x of the bulk value, so 3 times higher than the bulk resistivity. And this is measured. This is resistivity, of course, measured over many wafers. Then we also, this is silver. We also have done gold. Gold is not easy to print, but this is gold, 4 nanometer gold. These lines, these channels are about 150 nanometer thick and need the 400C. We use rapid thermal processing or rapid thermal annealing. In this case, it's 400C for 1 minute, and it's less than 3x. It's about 2.8x of the bulk resistivity. You can do copper. This is copper. You can see this is 1 micron thick, and you can see it's the lines are pretty uniform. So a lot of people that print have trouble with the coffee ring effect. So coffee ring effect can be avoided because it's a function of evaporation and function of the surface tension. And you can see here that we've been able to avoid that. One of the companies we work with wanted us to fully print a touch display. So touch display is just a metal grid, like what you have in typical iPhone. Typical iPhone has copper lines. These lines are about 2 micron wide and 100 to 200 micron spacing, depending on the phone. But they wanted to print it. So and using silver. So we did print it using silver. And this is the 2 micron line, for example, and you can see here. And then they said, what about printing the lines at the nanoscale? So they're smaller than the wavelength of the visible wavelength. So that means you will not see them. And so we actually shown that you can actually print 300 nanometer lines, like you see here. And this is what the lines look like. And there was some concern about the line edge roughness for these printed structures. So you can see the line edge roughness is about 3.7 nanometers. And this is using large particles. So the performance with this touch display, for example, here, this is before annealing. This is the IV curve. And this is after annealing, for example. So you can see it's milliamp, which is what they wanted. And the transmittance of the light, you can see this was printed on PET, which is the same web that the iPhone uses. So this is bare PET, and then when we print the grid, of course, you can see barely decreased in transmission. This is the visible wavelength. You can also use this to make devices. So these are diodes. These are nanoscale diodes that are fully printed, and these are 2,6 semiconductor. These are zinc selenide, and zinc selenide can be used to emit blue light in a diode. So these 50 nanometer diode, you can see here this is the N type and this is the P type, and they emit blue light between 3 to 5 volts. So you can see here, you can see that at 3 volts, you can see it goes up, and it gives us blue wavelength. So this is a blue LED that is fully printed, self-annealed, no annealing required, by simply using zinc selenide, P and N-doped zinc selenide. In terms of the transistors, for example, we have done carbon nanotube-based transistors with aligned carbon nanotubes, for example. You can go up to 10 to the 6 on-off ratio. We have done heterogeneous materials. We've done inverters using single-wall carbon nanotube as the P type, and molybdenum disulfide 2D material as the N type. And we also have done organic electronics using single crystal organic electronics, which is C8BT. So I'm going to give you just quick examples. This is printed organic transistor, and when we print the organic transistor, we saw that it is a single crystal, and this is on-off ratio is about 10 to the 4th, which is not bad for an organic transistor. Then we said, what about if we forget about the gold here and use carbon nanotubes as the electrodes? So we did that, and these are done these are transferred. So you have the template, you have the ink template, and then printed on polyurethane. And so we can go up to 10 to the 5th RF ratio because the contact between the CNT and the organic semiconductor is much, much better. And then we did all carbon nanotube transistor, meaning the conductor is carbon nanotubes and the semiconductor is carbon nanotubes. And this was just published. And this one, we got 50% of the devices that have RF ratio 10 to the 5th or higher. So you can do a variety of things with this. It's very, very robust. It's a very good toolbox that you can actually utilize to do a variety of devices. Here we have, these are transistors using 2,6 semiconductor. And so this is zinc oxide. So you can see before and after annealing, and the RF ratio here is 10 to the 5th. And the devices where we use devices that with the varying dimensions. So the channel width, for example, was varied from 2 micron to 100 nanometer, and the length from 20 micron to 100 nanometer. So you can see that we can print actually very small structures on the same substrate. The other application is sensors. So I'm going to talk a little bit about sensors. I'm only going to focus on a couple: the chemical sensor and the sensor for glucose and lactate in sweat. But we've done a variety of sensors for bacteria, viruses, for cancer, and a variety of and for alcohol and chemicals and so forth. So this is a chemical sensor that uses semiconducting carbon nanotubes that are functionalized by tempo or 4 amino tempo molecule, and it's a resistive, chemioresistive sensor. And so basically, if you detect the hydrogen sulfide, the resistance will go up, which means the current will go down. And then when the hydrogen sulfide gas goes away, the sensor recovers. So the sensor actually has a baseline resistance that's always stable. And we had one sensor that we tested for 2 years in a row and was always stable. We also use the same channel, but this time it's a conductive carbon nanotube channel. And in this case, we used it to detect glucose, lactate, and urea in sweat. And so you can see it's flexible material. It could be PET or PEN. And we can measure, you can see this is the glucose measurement, lactate, and urea. And this is later glucose measurements that you can see it's a very sharp, very good response, for example. We expanded on the lactate sensor. And you can see here, this is a lactate measurement in sweat. And you can see when you have a concentration, of course, the response is very good. The calibration curve is pretty linear. It is very specific. So when you functionalize lactate or glucose, you use glucose oxidase or lactate oxidase. And of course, it's very specific. And here, this is to look at specificity. And so here, this is uric acid. This is a lactate sensor. When you have lactate, of course, it responds. When you have glucose, there is no response, which is very specific. And to have low power, initially we were running the sensor at 100 millivolt. And so we wanted to reduce the power. And so we can actually run it at 20 millivolts with no issues. This was connected to a wireless low energy Bluetooth, so that the sensor will be connected to that and will be packaged with the microfluidics and will be touched with the skin. And then it will use the Bluetooth to send the data to the smartphone. And you can have a battery that will last for weeks, for example. And the sensor also will last for at least a week itself before you replace it. So now what we have done is we took all that and we put it together in one tool. And so this tool basically would have the alignment, would have lithography built in because we use lithography, has the assembly, everything is in that tool. And so basically you have a tool that's basically in your lab or your factory, and it's fully trusted, and you submit your design and then you can print. So for example, this is for a polyurethane. This is flexible electronics. By the way, the flexible tool is separate from the tool that prints on silicon and sapphires and other substrates. So they're really two different tools. One uses the template and one does not. So this is polyurethane. So you can see it's very flexible. And this is a line. So this is a gate and a channel underneath it. And the alignment basically is the minimum feature size 5 micron and the alignment accuracy is 2 micron. So this is 2 online layers printed down to the micro scale. We've done the same thing on wafers. This is 3 layers on wafers. So this is the source and drain. This is the gate dielectric, and this is the gate. And you can see, so the gate is 2 micron, and the gap between the source and drain is 2 microns. So you can see it's exactly over that. So that's done completely automated with the tool. So the tool has the capability to do alignment automatically. So basically, this tool has you can do any material or any substrate. We didn't try every material, but we tried a lot of materials. Minimum feature size is 20 nanometer. That actually is, if you have lithography that does that, the tool that we have here can go down to 600 nanometers with alignment at 600 nanometers. It's very inexpensive compared to conventional fabrications, about 10 to 100x. High throughput is about 10 to 100x faster. So in closing, I've shown you 3 different unique technologies that can enable you to do printing of features ranging from nanometers to hundreds of microns. You can print any material on any substrate, organic or inorganic. You can actually you can print crystalline structures for metal and semiconductors at low temperature. It's high throughput, like we said. You can print 1 layer per minute on wafers. It can print 1,000 times smaller and 1,000 times faster than inkjet. And the electronics, of course, is done at ambient temperature and pressure. There is no vacuum used except for the vacuum for the robot in the factor. You have to use vacuum for that, but there's no vacuum is used anywhere else. And the bottom line is actually it allows the circuit designer to have endless material choices, whether it's nanomaterials or 2D material, 1D material, particles, any new material can be used using this technology. You don't have to actually, conventional fabrication does not give you that luxury. This one it gives you versatile choices, for example, and you can make up your own material and use it. So let me acknowledge the support by the National Science Foundation, Air Force, a lot of companies, Analog, DARPA, NASA, and a variety of other companies. So I'll stop here and see if you have any questions.
Thank you so much, Ahmed. I think this is what you talked about is a very important issue at this point in time, especially with what's happening in the United States in terms of this push for going back to fabrication of its own chips. So my question to you, I will start the question here, but is how do you see this revival of microfabrication, and where do you see your technology playing a role in this news that we hear about what's going in the US?
Yeah, I think this is exactly right. The US is actually have a bill proposed 250 billion in one Senate bill, for example. That's unheard of. That never happened before in the United States. So basically, we're very hopeful that they will not only invest in conventional fabrication, but also invest in new technology. And so basically, we can actually take an 8088 to 386 and make it right now. Now, most people are young here, so nobody remembers the 8088, the first PC. But the 8088 actually was just 3 to 4 layers and about 3 micron minimum feature size, for example. Just to remind you. But we're very enthusiastic because now we, by the way, we're a tool will be installed before the end of the year in the United Kingdom. So the first tool, this is a flexible electronics tool. So we think that this is the way to go, really, because you're now down to about 5 companies that do semiconductor manufacturing, and everybody's worried about the supply chain, right? And security. The Department of Defense is completely, worried about the security. So this allows the security, but not only that, you can use quantum dots, you can use any 2D material you want, you can use, and in your circuit, no one knows what your circuit is. There's a whole division of the government that worries about hardware Trojans. These are hardware Trojans that are embedded into chips that are made somewhere else. Okay. Yeah.
You don't want to say the counter, but okay.
Yeah.
So one piece of news, I don't know if you know, but it was announced that Global Foundries is going to invest $4 billion in Singapore for a new chip production.
Yeah.
I don't know if you know about
this is nice. A good friend of mine is a senior VP at Global Foundries, and actually, I still have a lot of my students at Global Foundries. So it's a good company. It's coming around,
Yeah.
Global Foundry, for those who do not know, Global Foundry is the manufacturing arm of Advanced Micro Devices.
Yeah.
I used to help them with their fab. Back they have fabs in Austin and in Germany, and now they have it in New York.
And now they're coming to Singapore.
That's right.
So let me look at some questions from the people here. People can write their questions by pressing the button Q&A. So Andrew Wee is asking, can you explain how 2D materials can be deposited by inkjet?
Okay, we don't use inkjet. So that's number one. What we do is we directed assembly. So each 2D material is basically you apply either electrophoretic force if there's a charge on it. If there's no charge, you can apply electrophoretic force, or you can apply convective assembly or fast fluidic. Either one would work with 2D materials. Inkjet, what they do is they make an ink, and then they just use droplets that are impacted on the surface, and you don't really have much control over it once it hits the surface. We control each element, each nano element by itself.
Okay, good. So I have another question here from Salim El Kazi. I guess it's related to the beginning of your talk. Mm-hmm. Why do you apply 2 volts?
Okay.
The question is, why do you apply 2 volts? How do you choose the voltage?
That's a very good question, actually. So the assembly, I was teaching a class this morning about new techniques in nanomanufacturing, and this was actually one of the topics. So when you use electrophoresis or dielectrophoresis, you have a force that controls your directed assembly. So this force depends on if using the electrophoresis, which is applying a DC volts, for example. So your variables are the charge, the particle charge, or the voltage, and time, and concentration. And so basically the main driving mechanism that drives the particle to the wafer is the electrophoretic force. The electrophoretic force is a function of the voltage, the particle charge, and that's it. And so the higher the voltage, the higher the force, and the better assembly, and the faster assembly you have. So you choose that based on your particle charge and based on the type of particle. You can actually use a higher voltage if you want, up to 3 volts or so. We don't really go above 3 volts. Or you can increase the charge, increase the potential on the particle, so that allows you to use lower voltage, for example. So it depends on how much electrophoretic force you need to apply.
Okay. I have another question here from Wenyu Jiang. With high aspect ratio, for instance, 4 nanometers width, 150 nanometer thickness height, is the nanopillar mechanically strong? And then he says, can dielectric, like silicon dioxide, be deposited this way?
So the first question, I would say probably not. We have not made structures. We've done assembly in vias that deep, but we have not made 3D structures and tested them mechanically. Mostly we test the electrical characterization or metallic characterization, but not mechanical, strength. So we have not done that. But looking at the dimensions, I would say it will not be mechanically strong.
Okay.
It depends on what force you apply to it.
Right.
That's number one. Dielectric, yes, absolutely. We've done a lot of silicon dioxide and other dielectric pillars, so that's straightforward. Is CMP still needed? We don't know. I can tell you that you can do 3-4 layers or more without CMP. If you, so I got asked that question before. So I know that up to 4 layers you don't need CMP. We have not done more than 4 or 5 layers. If you do 10 or 20, do you need CMP? I don't know. But if you need CMP, you can always apply it.
Yeah. Okay. So now Yungcha Jin is asking, how do you control the growth of metal bump only vertically, not in the transverse direction?
That's a good question. So it depends on what the patterning is. So sometimes you have functionalization on the surface of the wafer, for example, and this functionalization is only 1 nanometer or 2 nanometers thick. So you only wet the area that is not functionalized, and so the ink would not go anywhere. So that basically stays there. So that's one control. If you want to make a pillar, you have to have something that will hold it. So in this case, you need something. It could be a via it could be photoresist, or that you remove afterwards, or it could be you do the assembly in via in a silicon dioxide or silicon nitride or whatever that your dielectric is, and you can do the via inside. So in both cases, the ink will not go sideways.
Okay. Have you done any reliability tests to see the metal diffusion of your assembly metal pattern when contact with other materials? So asking about the diffusion in this process.
I mean, we have not done really high temperature diffusion. I think we went up to 100 degrees or so, maybe a little bit more than 100 degrees. So we know that that's not an issue. One thing that I want to say is that the metal diffusion problem, it's the material is the material. So whatever metal diffusion problems the conventional industry has, it should be the same. Okay, we don't really have any special material. We're using the same material, except that we use the material, the feedstock is different, and the process is different. But the product is pretty much the same at the end, unless you're using new materials like 2D material or nanowires or so forth. Then it's very different. But if you're using,
So actually, there is a question about this. How do you take care? Sinu Matthew asking, how do you take care of the wrinkling of monolayers of 2D materials during this printing? The issue of large ratios, right?
So typically, ideally, you want the nanomaterials to be within certain range. For example, let's say I want my flakes, whether it's molybdenum disulfide or whatever it is, I want them to be, let's say, if I'm doing microscale, I want them to be between, let's say, 5 and 10 micron, for example, in between. And then I can design my circuit so that I accommodate each one of them. And then I can land the 2D material in there, and I can print the electrodes on top, the source and drain on top of that, for example. If I'm doing nano, then I still want the same thing. I still want them to be, let's say, between 100 nanometer or 200 nanometers. This is just examples, by the way. You can adjust your source and drain gap to whatever nano, but you want them to have a narrower size distribution. You do not want them to be, to go all the way from hundreds of microns to 100 nanometers. That does not work. And you can actually do there's a lot of techniques to do this separation. So even if you have a mixed solution, it's not difficult actually to have a narrow size distribution. Right? Colloid chemists do it all the time.
Okay. So one more question here. For 1 minute, one printing, what's the overall size versus the smallest dimension?
That's a
By
very good question.
Haidong Liang.
Yeah, so that's a very good question. So we have done basically we've done larger than 4-inch, but most of the stuff that we work with is really 4-inch. So we can do 4-inch. We have done 4-inch down to submicron, and it's still 1 minute.
Okay. So, well, Kalu, Kalu could ask this question in person, but okay. Kalu is asking, what can be the lowest thickness of gate oxide printed with this type of printing technique, and how the breakdown voltage may compare with the conventional thermal or CVD deposition?
So if you want to have a really, really thin gate oxide, I would use ALD. Okay, if I went to 1 nanometer, it's really hard to actually get a continuous film. It can be done. It's just it's a little bit difficult. However, you can actually use hafnium oxide particles, and you can anneal them, and you can have a thin gate. It would not be 1 nanometer, but it would be maybe a few nanometers, and that will give you a pretty good gate oxide. We have not done that. Other people have done this. They deposited hafnium oxide particles and they annealed them, and they got a nice dielectric layer out of that. We have not done that.
Okay. One last question here from Santanu Mohapatra. Is there any scope for small scale manufacturing for new companies?
Yeah, actually, our goal from the very beginning is to democratize manufacturing. So if you want to build your own devices and make your own devices, for example, you don't need a $20 billion fab. You can build a fab for 5 to 10 million, you know, and that includes packaging as well, you know. So this means that small companies can do it, as well as medium-sized companies can do it, and any research lab can do it. You know, I'm not talking about just universities, government research labs and industry research labs and so forth. Everybody can actually participate. Everybody can actually print their own nanotechnology. They don't need to buy, you know, a $10 million tool from Applied Materials or $50 million tool from somewhere else. You know, it makes it affordable. And by the way, it's very eco manufacturing because it uses very little water, it uses very little power, and it does not, you know, there's no vacuum. And actually, we published a paper on looking at the embodied energy. So people who do life cycle of materials and products, when they calculate the cost, the embodied energy, how much energy did it go in your process? They don't just look at the process. They look at how much energy did it take to produce the gas you're using? How much energy did it take to make the machine you're using? So we did this for one of the older processes, and we actually are 10 times lower energy than conventional manufacturing. And when we did the fast fluidic, we did the calculation again, and 25 times less embodied energy in this process.
Okay, fantastic. Thank you so much, Ahmed. Are there more questions from our panelists, or?
Yeah.
I have a couple, but maybe Ben, you can go first.
Oh, sure. Thank you. It was a wonderful talk, and I think I heard your talk. I think last year, and with Aaron as well. It was really interesting, and you've really done some really exciting stuff more recently. So you know, I think there's a strategy for, as you mentioned, big companies scaling up and using a lot of resources to build huge wafer scale manufacturing, right? Much larger. Maybe they're going to what? Much larger than 16-inch or something, 20-inch. But it looks like your strategy is going to, you know, fairly small, so 4-inch, but high throughput. Is that sort of what you're thinking of when you design the system to sort of maintain it at a 4-inch to less than 10-inch kind of scale?
No, actually, not at all. Actually, you can easily do 8-inch. It's just that it's cheaper for us to actually use 4-inch. Yeah. We're still small. We're still the university, and we have even the company that we started that makes the tools still use 4-inch. But you know, it's I would say, for example, in 1 minute, 4-inch wafer, 8-inch wafer would probably be 1.5 minutes or so. It would be a little bit more time. But the process works exactly the same. So you can go, you want to go 12 inch, you can go 12 inch actually. It's not a problem.
Okay, and you okay. So in terms of the uniformity, it's actually better than sort of almost other types of deposition methods, I assume.
See, I worked, this is a good question. I actually worked with IBM back in 1985 and 86 when IBM went from 5 inch to 8 inch. And I remember back then, they ordered the equipment from Applied, from Novellus and all these guys, and they got the equipment and the equipment did not work. And so I came in and we did modeling, we did flow visualization, we did all stuff and we scaled it. It turns out that the guys that were doing the building the equipment, they just scaled the geometry. They did not scale the process. And so IBM scaled the process and then gave it to all the companies. The companies turned around and sold it to everybody else. But basically the process, this process was because we actually developed these processes. So this was always in my mind. I did not want a process that was not scalable. And scalable means that all the gradient, all the concentration has to be the same everywhere. So basically when we applied, there's a line, the assembly goes through a line. So, you know, if the water level is like this, then everything through at that line is all the same, whether you have 4 inch or 8 inch or 12 inch.
I see. Wow. Yeah. Exciting. Cool stuff. All right. Go ahead. Go ahead, Shafiq. Thanks. Thank you.
Again, this is not my area of expertise, but one slide caught my attention where you said that 50% of your samples had over 10 to the 5 on-off ratio, which suggests that 50% didn't. What's the reliability of the process compared to other fabrication methods?
So there's 2 reasons for that. The first reason is my student Salman, who now works at Intel, did not use an aligner. He eyeballed his alignment. so a lot of his devices were not working properly. There was a problem with the alignment and he wanted to do it quickly, so that's what he did. But the other reason also is we're using mixed semiconducting nanotubes. We're not using 99.9% semiconducting nanotubes. These are mixed nanotubes. So basically you definitely will get 10 to the 2, 10 to the 3, 10 to the 7, depending on what nanotubes you have. We are working now on a new technique that actually based on something we published 10 years ago, that I think we can actually use carbon nanotubes and using some techniques without actually, so we use something like, 99.99 from like Nanointegris, for example. And by doing alignment, you can actually get very high semiconducting property. And more importantly, you will not get any short in any, these guys, what's his name? Shakrali and what's the guy's name? Phil. The one that was at IBM and now at Stanford, I forgot his name, and now at TSMC. Philip Wong. Philip Wong, yes, yeah. That's right. So they did a project together, just about ended about a year ago from DARPA. It was a $50 million project. And what they did is they did carbon nanotubes. They did 12-inch wafers everywhere, and they ran into a big problem. Even though they were using 99.99 from Nanointegris, they still had hundreds of thousands of transistors that were not working. Because even though you have only 0.001% and you're making billion transistors, you still have a large number. And so what they did is they used software to get around the defective ones. And that did not really eventually work. We found a way where we can actually, because they don't do assembly, they just do coding, random carbon nanotube coding. So if you have any metallic nanotubes, if they land anywhere, they're going to cause problems. And that's what happened with them. But I think with alignment, which we can do with direct assembly, we can avoid the conductive nanotubes, if there are any. And then basically the alignment also increases your semiconducting property. We published a paper on that 10 years ago in ACS Nano.
So one last question from me. So the obvious advantages of using new materials and it being much cheaper, I understand. But if you look at the traditional ways of sort of getting smaller and faster, that's what Global Foundries and TSMC are doing. Imagine a world where we decide that's too expensive and we instead go with these faster printing methods. What would that look like for computing?
It should not change very much, I would say, because we're using, assuming that we're not going to use the materials, okay? Assuming that we use the same material, you can actually get the same property, electronic property. You can get the same scale. There's no reason you cannot get the same. So you will not suffer. You'll just be paying $50 for an iPhone instead of $1,000, for example. That would be the big difference. But the performance should not suffer. Now the performance could be better because you could use 2D materials, you could use quantum dots, you can use other materials. I mean, you could imagine. We actually designed a tool. We didn't do it. We didn't make it. We designed a tool where you have the magic angle between 2D, so you can look up the angle and then you can actually pick it up, put one in, pick up the one, and twist it exactly like 0.1 degree and so forth. Even if these flakes are about 10 micron, you can still pick it up and actually rotate it and you get superconductivity if possible. So actually, all these things are possible, and it would open the door. I mean, look at the quantum computing now. All the quantum computers work at cryogenic temperatures, right? Is that practical? No, it's not practical. This is what Cray was doing 35 years ago. All cryogenic temperatures, for example. And now we're doing quantum computing with cryogenic temperatures. I think that the way people are going at quantum computing is going to completely change. And it's going to be a lot cheaper as well.
Wow. With that, I think it's a wonderful way to wrap up this seminar. I really love the discussion. I think it's very important for the moment we're living. So thank you so much, Ahmed, for this. I'm sure everybody enjoyed. And I, Shafiq, and Ben have to run to a to a meeting. So thank you so much. Thank you, everybody, for being here. And see you soon. Bye.
Thank you.
Okay, bye-bye.